Okay, welcome to my session, my talk, Uncursing the Ncurses. Today I'm going to tell you a bit our story into finding some vulnerabilities into this complex and open source library. My name is Emanuele, if you wonder who I am and where do I come from. So I work for Microsoft in the threat intelligence team, and I work as a security researcher in a team which is a bit particular. We are the cross-plat research team. So we don't deal only with Windows. We also think about and protect Linux machines, macOS, and mobile platforms, Android and iOS. Before Microsoft, I did a PhD in a research center in France, where, since I was talking about cross-plat and other platforms, well, I worked on binary analysis for Linux and IoT malware. And this is my professional side. For the less professional and, let's say, my kid side, I always loved reverse engineering. Always played tons of CTFs in team and in solo, reversing and exploring more exotic architectures, so from ARM to PowerPC, Motorola, MIPS, and so on. And recently, I said, I need some more fun. So I need to do some kind of switch. So I jumped into hardware, where I'm still exploring my way into reversing ICs, going up to firmware. And this work, it's the outcome of me and other teammates from my team in Microsoft, Jonathan But-Orr, Michael Pierce, Alexia Wilson, which unfortunately couldn't travel here, so that's it. What we are going to do today. Our journey into Ncurses. So I don't want to talk just about the vulnerability, but I want to tell you this story, which is our full journey. So from the start to the actual results. And for people not knowing or maybe not expert of Ncurses, I will give you a quick introduction, and then we'll jump straight into the details. So the vulnerabilities, how Ncurses work, and how we found them. We will have a close look, and we will conclude with the fix and the conclusion. Now, assume you have a challenge. You have a very short time, a very limited amount of time, let's say 1 day, 2 days, or 1 week at most. And you need to target something. You need to find the security issues, a vulnerability. You want to escalate privileges. You want to get root on that machine, starting from that application you are targeting. So here you can do many things. You can pick up a very complex software. You can go crazy about an exploit chain that you want to build to pawn that system. What we did instead was to start from the basics. We say, let's try to catch up all the low-hanging fruit and see where we can go in this very, very short time. First thing we can try, set UID binaries. These are very known, very typical and common. What is set UID? So it's this permission bit which you set over a file owned by a privileged user, so that you, as a privileged user, can execute it in the same way. So the moment you execute this binary, you will escalate your privileges for a limited amount of time. So to give you an example, you have this file which is owned by root. Assume you don't have the set UID bit. If the permissions for that file are not relaxed enough, you will get an error. You won't be able to execute it. But if the set UID bit is set, then as user, you will escalate. And this can be a bit of an issue if the code was not reviewed appropriately, or there are many things that might go wrong at this point. And what I did was to search for past vulnerabilities in SetUID binaries, search a bit the history of CVEs related to SetUID binaries. And there are some. There are many CVs. I just wanted to report the most recent, starting from 2001 with Qualys doing great work on heap-based overflow in sudo. And then another CV affecting Polkit with an out-of-bounds write, and going to more recent time with other unsanitized environment problems, policies bypasses. So we have a big set of suid-related problems. If you look at them more closely, you open this CV, you read a bit of the details, and you try to understand what's going on. There is one common factor in all of them. There is an intersection. All of them uses trampoline environment variables. So we just say suid might be problematic. Now we also say environment variables might be problematic. And in fact, in all of these CVs, they use it to control the memory, to inject commands, and finally isolate the privileges. And we know that normally we want to sanitize, we want to drop in sensitive scopes this kind of variable. So we say, let's start with suid. Let's see where we can go. We just did a simple find search on Linux and Mac. These are our targets. So for Linux, we are using Ubuntu. Mac, we are on latest macOS version. At that time, it was Ventura, I think, 13.5. And we got this simple list. If you look at it, there are tools which are very small, famous. There is one difference, which is on the first line on both screenshots. It's top. So top on macOS, top is for listening processes. It's for monitoring resources, CPU usage, memory usage. Top on macOS, it's suid. It's appearing on that list. So you see, at this point, top just became our new target because this was totally unexpected. On Linux, it's not suid. So we got a target. We do some static analysis, and we see that top is dynamically linked on both platforms. And now, on top of suid bit and environment variables, we have a new degree of complexity. Because at this point, if we also use third-party dependencies, who is responsible, for example, for clearing the environment? Me, creating my user code, I don't know what the library is doing in details. While the library doesn't know what I'm doing. So who is responsible for doing a full clear env? Who is responsible for clearing the environment completely? And the other question is, assuming I know this dependency I'm using very well, but at which point in time I'm going to clear the environment? Because we can have weird situations where me as user, by user I mean responsible for the code I wrote, I say, now it's the time to clear the environment. But then it's possible that the library will use it after, or there is a dependency. And I could break everything potentially. So this is, I would say, an art problem. It's something a bit tough. And the only things that we know are common practices. So we know that we should drop privileges as soon as possible. We know that we must be really aware of the third-party dependencies we are using. We must know them, and we must limit the usage if we can. Now we are slowly approaching Ncurses, and in fact, if we go back to the screenshots of the shared libraries we found linked in top on Ubuntu and macOS, we see that top on Mac is using lib Ncurses. Top on Linux is using system libraries plus other dependencies plus lib tinfo. Tinfo stands for terminfo. We'll soon talk about it, and it's a small library which is still part of Ncurses. So we can conclude that both binaries on both platforms are using Ncurses. And what is Ncurses? I think you are all familiar with this screenshot. It's just pure Linux kernel configuration page. And it's pretty fancy. You have a window, you have pages, you can, and this is all on the terminal, by the way. You can scroll up, down, you can select options. This is what Ncurses allows you, not only, but this is something that Ncurses allows you to do. And this screenshot is pretty old. It's from kernel version 2.6. We are way above that version. But just to tell you that also Ncurses is old as well. So Ncurses, it's an open source library that you use to create TUI application, to design your text-based user interfaces. A bit of history, just to contextualize it. It's pretty old. It's turning 30 this year, was forked in 93, almost my age. Before Ncurses, there was pcurses in 1982. Before that, the original product, like the first instance of Curses was in 1978. There were other attempts in parallel, which I would say didn't have that much success, like pdcurses, pccurses, ntcurses, but we just want to focus on Ncurses. I hope this timeline is accurate. It was pretty difficult to find all these tiny forks and version, but should be pretty precise. And if you go over the man page for Ncurses, you will just get a glimpse, an idea on how powerful this library is, because in fact, starting from 95, it's used in the Linux kernel. It's used in almost every Unix system, every BSD system. It's also used in macOS, and there are ports for Windows as well. So if we are able to target this, maybe we have potential to target a lot of different platforms. What you can do with it, this is a small snippet I wrote just for this talk. On the right, you have this small box. It was done with very few lines of code. This is the most basic example, the most basic thing you can do. But anyway, you have three portions in the code. First function, init str. Remember it. We will see it later. This is to init all the structures, to initialize the memory, and to prepare the terminal. Then you create your fancy layout. You can create windows, boxes, and once everything is ready, you have everything ready in the memory, just hit refresh. So at this point, you get everything to the terminal in the output. You can continue to play with it, and then at the end, super easy, end win, you tear down everything, and you are ready to restore your terminal, your previous TTY session. So this is pretty powerful. You remember the screenshot before from the Linux kernel configuration page? And you can do many things. So with in a terminal, you have different options, you have different features, you have different terminals. Remember, before terminals were hardware stuff. So now we are trying to bring this compatibility to modern systems, which are all software-based. But the terminal is controlled by something which is called capability. So this is a parallel wall way bigger than the terminal wall itself, because it's thanks to capabilities that you control the terminal. And where do you put these capabilities? In this terminfo file. Terminfo, it's basically a database. It's a comma-separated list of all these tiny capabilities that you can define. And you can define properties, supported operations, for example, what the terminal should do if you hit the key up on your keyboard, if you want to scroll up or down, or how many columns you have, or what is the bell control character on your terminal, or how many colors you can support, and so on, up to initialization strings and so many other stuff. And this list is made of 3 types. You have Boolean capabilities, example, which, by the way, capabilities are defined in this database by their short name, which is predefined. To give you an example, AM stands for, if I'm not wrong, auto margin, should be to tell your terminal that you support auto margins. Numeric capabilities, you recognize them because you have the short name, then that symbol, and then an integer. So calls 100, you define 100 columns. Colors 8, you support up to 8 colors. And then what I believe to be the most interesting set of capabilities, which are string capabilities. Here is just typical value variable assignment. You have the short name equal the control characters plus some other stuff. And here we go to the concept of parameterized string capabilities. So you have this concept because some capabilities accept, it's like they accept arguments. So take, for example, the cap capability. Cap is the short name. This is a capability to position your cursor into the terminal. So it needs coordinates, X and Y. And so it will accept row and column. So overall, these parameterized string capabilities are a stack-like, they follow a stack-like format. They are like printf. So like printf, they will support some interesting escapes. To give you an example, a couple of examples, here I reported some of them, not the full list, it's too big, but anyway, you can use % plus a number, you declare an integer constant. Then you can use %p with a number going from 1 to 9, then it means, look, push that heat parameter into this stack-like object. You have arithmetic operations, so if you have a plus, you will have a double pop from the stack, push of the final result. Bit operation, logical operations, and then since we follow, we kind of follow the printf format, we also have %cs to pop character or string, dx to pop an integer or an hexadecimal. So I mentioned cap before. Cap accepts row and column, so 2 digits, 2 numbers. If you write the capability in that info file as %p1d, %p2d, it means push the first one and take it as integer, push the second one, take it as an integer. Now, we know how to write our own terminfo database, and what we must know is that terminfo, when it's used by Ncurses, and when it's used in general, it's actually compiled. So we need to compile this text that we wrote. We can use stick, this tiny utility which is part of Ncurses. And if we want, like we want to analyze a terminal definition that we already have on our machine. On our boxes, Linux, Mac, we already have predefined definitions. So if we want to decompile them and look into them, we can use infocmp. This is just an example of, in the screenshots of the infocmp output, you see what we just said. So you have the capabilities, string capabilities, everything is comma separated, and that's it. Now, we know about this terminfo file. This is something we control because we can create our own terminal, we can define our own terminal. We need to see if there is a way to push it in our programs, if we can force the programs we want to target to load it. And man pages are, again, pretty helpful. And in fact, from the man page, you can read the Ncurses library searches for terminal descriptions in several places, which is super cool for us. But even more important, it says this place can be overridden by environment variables. So you can use terminfo equal and a string of the path pointing to your control terminfo database to load it, which is what we did for the whole exercise. But let's assume you cannot use or you don't want to use environment variables. Ncurses will try to grab your terminal definition from the .terminfo file in your home directory, so without using environment variables. And you remember that small snippet of code. I told you, remember init SCR. So that was the initialization routine. If we check it in GDB or any debugger, we follow the stack trace. We go up to NC read entry, stands for Ncurses read entry. This is the entry point for the actual parser. So something we will inspect a bit more in depth, because if there is a parser for a binary file, it means we know very well that the probabilities that something could go wrong there is pretty high for historical reasons. I mean, parsers are known to be dangerous to handle. And eventually, we also find a reference to our custom compiled terminfo file. So under temp, cars, x, and then the name of the terminal. Now we are ready for this research. We want to start to find something. So there are a lot of research pointers. First one, capabilities are predefined, and we have over 400 different capabilities. We tried to look into them to see if there was something powerful enough, let's say, and we found 3 capabilities which are really powerful. First one, IF, name of an initialization file. So you put this capability in your terminfo file. If you want your terminal to print whatever file you define during initialization phase, to print it to standard output. Then you have RF, exactly the same, but for reset file. So when you tear down your terminal, again, put the content of that file to standard output. And then you have the one which is maybe the most powerful you could find, we could find, which is iprog, path name of a program for initialization. So this is curious. Basically, if you define iprog capability, it means as soon as your terminal starts, it will execute whatever binary you choose, which is a very powerful primitive, because if you can find a program using this iprog, it means you could get, in theory, escalation for free. Unfortunately, it was not the case for top. It's not using any of these. We found that there are a couple of small, very tiny applications using them, but there is not much you can do. Like, if it don't go wrong, there is tput and something else, but that's it. Then there is the concept of extended capabilities. You can create your new capabilities, you can create your new terminal, but this was a dead end because top was not using these extended capabilities. There was nothing interesting over there. As I said before, the parser. This could be a juicy target. And last pointer we defined, research pointer we defined, are parameterized capabilities. So we said these capabilities are like, they behave like printf. So it means we know how format tag strings work. We can try to mimic them and see if it will work. So we went with the last 2 points in this list. We discarded the first because, again, remember, the challenge here is to get the most, achieve the most in a very short time. Now, before jumping into the code details and the bugs, I think it would make sense to explain you how the terminfo file format works and how you can build it. I'm talking about the compiled version because it's useful to understand the vulnerabilities we found. So we start with this file, which could be up to, if I'm not wrong, up to 1 page, 4 kilobytes in length. First section is made of 12 bytes, the header. In the header, you have the magic. This part is curious. So the magic can get 2 values. You use one to define, to declare compiled 16-bit entries, and one for 32-bit entries. So the 32-bit entries, it's kind of a newer support, but we couldn't use it because our target is macOS, is stopped there, which is suid. And what we found out is that Apple is using an older version of Ncurses, so there was no support at all. So eventually, we had to go for the Octal 0432 version. Then you have name size, which is the length of the string where you declare your terminal name. And then basically you declare the size of the arrays storing Boolean, numerical, and string capabilities. So bool count, num count, string count. And actually, in the array for string capabilities, you have the offset into the string table, which comes after. So the string table is where you will actually go to fetch the value. And this is for the predefined capabilities. We say that we can extend the capabilities, which is optional, and you must have support in the code. You must compile Ncurses with extended capability support. So you have another section which is pretty much the same and following the previous section, which I just explained. So you have the extended header with extended bools, extended number of extended count for numbers, for strings, and again the string table. Now, what do you write in these arrays? How do you create them? For Booleans, it's easy, 0, 1. For numbers, you can either put the values you want to assign to that capability, to that variable, or -1 or -2. -1 to declare an absent numeric, -2 cancel numeric. So we have this concept for capabilities we really don't want to consider, and I will tell you why soon. And same for strings. The only difference with strings is that since it's an offset in the string table, you must be sure that this offset is not going beyond the string table itself. So there is this small check. If the offset is bigger than the size of the string table, convert the capability to absent string. So why we have absent and cancel? Because thing is, if you want to declare a capability, you need to declare, since they are predefined. So imagine capabilities as a fixed array. So you say, I want to declare the 5th capability, predefined capability. You need to declare all of them up to the 5th. So assuming you want to declare the 5th Boolean, you will put in that Boolean's vector 0, 0, 0, 0, 1. So you just declare all of them. Same for numerical. If you want to pick the second numerical capability, you will put -1 maybe for the first or whatever, and then the value you want to assign. Now I'm saying you pick the 5th, you pick the second just because I don't remember the mapping. You have a precise mapping between the short name and the X index in this predefined array. And last very tiny detail, just to do not miss it, is that everything, since we are using the magic for 16 bits compiled entries, everything is aligned to shorts. So after the terminal name, the string, plus the Booleans, since they are stored on bytes, you might need to add some padding in case the last Boolean capability ends over an odd byte, so that you can realign everything. And the same after the string table, especially if you use the extended capabilities. Now, it's time for the actual work. And we follow 2 ways. First one, manual auditing. Second one, just fuzzing. We pull the latest code. At the time of this project was version 6.4, patch level 0311, so 11th of March. And then we also found that Mac has its own version of Ncurses available in their account on GitHub. But the confusing part was that, for sure, we wanted to use the same version, both on Linux and Mac if possible. But on Mac, we found references to Ncurses 5.4, which is very, very old. So it was a bit strange. Ncurses 6.1, but again, we don't know, it doesn't match the upstream code for Ncurses 6.1. And then finally, graphing a bit here and there in the actual code, we found the same versioning string used by Ncurses maintainer. And we assume that Apple was using version 5.7, which is just 15 years older than upstream Ncurses. But one thing to mention is that anyway, they backported some patches also for the CV, so they try to stay up to date anyway. Now we need the fuzzing harness, and it's not a fuzzing talk, so I'm not going to the details, but we write some code with some optimization here and there to fuzz the NC read entry, which is the entry point for the terminfo parser, and we pulled and compiled everything with FL++, but with other sanitizer support, which revealed to be very important for us since many overflows were just silent. And since our target is Mac, we did this research beside the fuzzing, which happened on Linux. We did this research on both Mac and Ubuntu, especially for the triage part of the corpus we obtained. So, first bug, heap-based buffer overflow. How does it work? We are in the function readTerm type, and Ncurses, it already opened the terminfo database, which we created. It parses the header, booleans, numerical capabilities, and now it's time for the strings. So we have the first call at line 5, the calloc to create this array of strings capabilities. What is the length? The maximum between the string count, which we control, it's in the header of the terminfo, and this other capital string count, which in theory is the maximum number of allowed string capabilities, which should be 414. But since we control it, we just put a bigger number, and we can bypass the number of predefined capabilities. And now we have this chunk of memory into the heap. Then the code will continue. We will call another function, which is convert strings, to do the actual parsing once the memory is allocated and put everything there onto the heap. Then it checks if there is support for, if we have extended strings. As I say, extended support is optional, but we have it. And we need a bigger memory chunk. So there is a realloc. But what is the issue is that this realloc is done without taking into account the fact that this number of string capabilities that we control is way higher than the maximum allowed number of string capabilities. So line 12, you see that num strings is equal to string count in capital letters plus number of extended string capabilities. So the whole concept of string count, string capabilities not extended ones is gone away. And final result of this realloc is that we are shrinking the memory. So we have a smaller chunk now. What is the issue? That later we need to parse everything and put everything in memory. We are writing to the strings pointer, which is still there, plus string count, but there is, I mean, the chunk of memory that we have now doesn't cover everything we want to do. So we basically just write out of bounds. And running this, just the POC will basically crash everywhere. We played a bit with it to try to do more, especially on Linux, and we were able to corrupt the heap and tons of metadata like the top sides or the unsorted bins. We tried to play it also with other bins. So this is pretty powerful where you have some degree of control. Second bug, stack leak. So here we move to another function. It's called tparm. Tparm, it's used to handle these parameterized string capabilities. So it's running the capability logic. And these string capabilities, we say that they are like printf. So also typarm is a variadic function, like printf. Assume you have a format string with some encodings. You don't know how many parameters your printf actually needs. So you end up using the var start, var arg, and all these things so that you can consume the stack. But format string attack. So what happens in printf if we write a format string expecting more parameters, but we only declare one, so %s and then xxx, and we only pass the string AA. It will print AA and will pull all the rest from the stack. So in printf case, it's powerful because you can control the read, you can control also the write if you want. In Ncurses case, take as an example cap, the one we mentioned before to control the cursor in your terminal. If you use %p, encoding with a number, consuming all the numbers you can, so p1, p2, up to 9, even if the capability only accepts a smaller amount of argument, like a cap as 2 rows and columns, well, final result, and then if you put something to print it, to pop from the struct, like in this case, %x for hexadecimal format, the result is that you have a full leak, like it would happen for printf, which again is pretty powerful because in context of info leak and, I don't know, SLR bypass, this is another primitive which you could use. Then we move to the third bug, which we call type confusion. So we say that parameterized string capabilities, they are stuck like objects, but truth is that this stack is made of, it's working over an array made of 20 stack frames. Now, each stack frame can be a number or a string. It's basically a union. This struct is a union. But how do you know if the argument, the parameter you expect is a number or a character, for example? So normally you can walk the format string statically to infer the type. It's easy sometimes. Like you have a %s. You say, done, it's a string. %d, easy, it's a number. But what if you encounter %p? That encoding to push into the stack. You have no knowledge. You don't know the type, if it's a number or a string. And that's why in the code, you have this heuristic to try to infer the type of that specific capability, that specific parameter. And for P, for P in particular, you have this array, P is S. So how it works, if after %P, you find, I don't know, %S, something that is related to strings, you will conclude that that parameter might be, I mean, not might be, will be a string. If it's D, for example, then that parameter, for sure, it's a digit, it's a number. Now, small example, what happens if you force the other way around? So you know that the capability wants a digit, but you consume that digit, that number as a string. So again, since we are always using cap as an example, what if we declare cap with %p, %s instead of d? Result is that will be handled as a string, so we'll call string length over a number, everything will explode and will crash. Now, we don't have much time to go all over the bugs. It's almost lunchtime. I need to conclude. So there are other bugs that we found. Some of them are just minor crashes, like dereferencing a -1. But the only true thing here is that I feel like we scratched the tip of this surface with the fuzzers. And I'm saying this because code coverage was not great. And in fact, what we found was so easy to spot, was pretty immediate for whatever fuzzer you are using. And without fixing these bugs, you cannot explore more, but this is something which is known, and it's a problem for code coverage in general. And some of them would not have been possible without address sanitizer. There were silent overflows, everything was looking great, but it was not at the end eventually. And beside Ncurses, also Apple's top version is open source, available on GitHub on their page. We had a look at it as well, even if we just focused on Ncurses. And this research went just in parallel for both platforms. Now, for the disclosure, we started with Thomas Idiki, which is the principal maintainer, the historical Ncurses maintainer, which we thank a lot. It was really helpful, reactive, and he fixed everything in a very short time. We disclosed everything to Apple as well, to the OSS security mailing list, to all major Linux distributions, and we got a CV to put everything, all the bugs into this single bucket where it says that a set UID application may allow a local user to escalate privileges to corrupt the memory if using Ncurses and terminfo environment variable. But also, you can also avoid using it. As I said, you just use the .terminfo file in your own directory. Now, the fix, it was immediate for upstream Ncurses with patch 0408, patch level 0408, Ncurses 6.4. Changelog is improved checks for MAF4 terminfo data, while Apple fixed this in Ventura 13.5 with improved validation, because there were unexpected terminations or arbitrary code execution. So, to conclude, dealing with dependencies is tricky, and we touched dangerous factors like set IUD binaries, environment variables, libraries, and everyone would say, yes, but I need to build my software, I need to build my application, I need features, I need to do stuff. So it's hard to handle all of them, but the only thing we can do is to look out for this set ID bit. We drop it if we don't need it, or at least we drop privileges as soon as possible. We don't use the environment, we shouldn't use environment variables if we don't need them, or at least just clear whatever we can. And we should also be careful with files which are open and read not by us, but from that third-party dependency. So look at Ncurses. And to conclude, just 2 points. I wanted to bring this talk also to show you how third-party dependencies are important. So in this case, we targeted an open source library, which is used everywhere. And one single bug, one single test case was triggering on Linux, Mac, everywhere there was that latest version of Ncurses. And then last but not least, what seems innocuous can be dangerous, and this was my surprise, basically. Take top. I always ignored top, always used it, and I didn't know that it was suid on Mac, which was the biggest surprise, and which was how everything started. So that was me, and I think after lunch or soon anyway, we will publish a blog post. If you want more details, everything will be written there. So thank you, and if you have questions, I'm here. Otherwise, I leave you free for lunch.